So we did tight binding, we did free electrons, and we said that everything in between can be understood as one of these models. They give us similar results, and basically they are our main tools to calculate the electronic properties of metals. Oh, and insulators. Okay, what I'm going to do today is some consequences of this behavior, and writing down actually what we have done in another language, the language of creation and annihilation operators. Not that it will give us any new discoveries or something different in the behavior of this system. It's just one thing, it's cool to see it in this way. Second, it's a good introduction to field theory for people who will continue to advance studies. And third, it's a very convenient way to think about solving these problems on a computer. Okay, so let's start. Basically, I will illustrate the main points for a two-dimensional simple cubic, but everything that I say could be applied to anything between 1 and 3D, well, actually any D system, and to any lattice structure. Some of them are more complicated than others. Okay, so let's assume that we are considering simple cubic lattice. First thing that I have to understand once I'm trying to understand what is happening for electrons in a simple cubic, and I'll do it two-dimension for simplicity. What is the first thing I'm checking? Quantum mechanics looks on electrons as waves. Waves, we have to know Brillouin zones, so I have to understand what is a Brillouin zone. That is the first step, no matter what I'm doing, merely free electrons or tight binding. Okay, so this is a simple cubic lattice. Hope I don't have to convince you that this is the correct way to write it. Okay, so basically I can come and plot the Brillouin zones. So I'll do it both for, well, at the moment it's the same Brillouin zone, but I would like to see what the implications are, nearly free electrons and tight binding. Okay, so these are the first Brillouin zones.
They look the same.
As I said, nothing changed. Brillouin zone is a property of the lattice, not of the approximation that I perform on the lattice, right? So, until here, you're right. They are the same. Where is the second Brillouin zone?
Find the next nearest neighbor.
Right. So first I'll put the nearest neighbor point, because this is not a nearest neighbor point. It's half the way to. A bit bigger. So these are the nearest neighbor points, and to remind you something that we did in the first class of the semester, Brillouin zone, which is basically primitive lattice unit. I draw lines to the nearest neighbors, mark the half, and draw a line perpendicular. So that's why, if you don't remember what, and if I'm doing it in real space or in reciprocal space, it doesn't matter. Same. Where are the next points?
The points it will be at the corners of the Brillouin zone will be at the nearest neighbor. No, the corners for the...
No, I want to put the next nearest neighbor point.
So it'll be at 2 pi a, 2 pi a, 2 pi a minus 2 pi a minus 2 pi a, 2 pi a minus 2 pi a minus 2 pi a.
Great.
That should be 2 pi a's.
So I'll replicate the drawing here. Okay, and I have so the next Brillouin zone will be okay, and if I would like to bore me to death, I could continue. Okay. Let's look what happens when we're considering really free electrons. Okay, what is the shape of the Fermi surface?
Sphere.
A sphere. So, if I have low filling, let's say half an electron per lattice point, a quarter or something, I'll have such a Brillouin zone. I have more electrons, I have a larger sphere. have more electrons, let's say over half filling. I'll start invading the second Brillouin zone. That's fine. There's no penalty to move to the second Brillouin zone. So, very simple, very clear. The only problem, it's not realistic because I ignored gaps. What does it mean that I have a gap? That moving from the first to the second Brillouin zone doesn't cost me only k. It's an additional constant, or an additional energy of U of on these first Brillouin zones. Okay. So I perform the calculation for a specific potential and get this value U. Okay, so what changed? Well, for the first and the second circle, nothing changed. But now for the third circle, it becomes more costly to transform the population into the second Brillouin zone, because then you pay plus U. So you don't. Or maybe you do, but you do it in a later stage. So instead of this symmetric circle, you will have as if you have some barrier here. It's not as if you have. And you fill up more in the first Brillouin zone before you move on to fill up on the second Brillouin zone.
But why are there lines in the gap?
There's here?
Down, the other one. Like that one.
This one? And this one?
Yeah.
Because at some point, going more and more in this direction is larger k, right? At some point, it will be less costly to pay this U and have a smaller k than to continue and fill up this region. So you don't. Okay. To really convince yourselves, one should do the calculation. Find each time the smallest k to fill up and see, for example, at what point it starts to cross into the second Brillouin zone. Now, this structure is very interesting. Let's look what happens actually here. At high filling, at low filling, it's trivial. It's free, behaves exactly as free electrons. But here, see, if I translate these three corners to here, okay, copy copy this guy to here, this guy to here, this guy to here. Effectively, I have a Fermi surface for an empty bubble. Okay, all this is filled, but these quarter pizza slices are empty. Now I'm just moving it because I'm always entitled to move by G. And I get a picture of a small Fermi surface, but in an opposite direction to what we are really usually used to. Instead of this is filled and these are empty, I get this is empty and these are filled. So I basically conclude that for these systems, once I'm close to full filling, I will actually have Fermi surfaces corresponding to holes in the first Brillouin zone, and if I stick these guys together,
And it becomes easier to count holes than.
and I'll have part of them are holes and part of them are electrons, and they can choose to live wherever it's convenient for them. So I get an intricate behavior here. On the other hand, if U is huge, we'll fill up the first Brillouin zone, never cross until you put in more and more energy, and then it will move to the second. So all behavior, if U approaches zero, it's just regular free electrons. If U is very large, you fill up Brillouin zone after Brillouin zone. If it's intermediate, you can have interesting behavior. Okay, so in a scheme to get more attendance here, I'm now giving this project to plot such a behavior for nearly free electrons. Choose U as you want, draw a few values of filling, and show this map. How to do it? You need some minor computer programming skills, not much. Anyone who, well, I'll take one volunteer to do it. It's 5 additional points in the course. Someone picking it up?
Would it need to be used, would the method use perturbation theory?
No, you don't need here anything, actually. What are you doing here? You are checking a point.
Yeah.
If you don't have anything to calculate because the whole behavior is in the first Brillouin zone, it's h bar k square over 2 pi.
You check if the energy is less than the Brillouin zone along the axis.
So you just fill up the first one. If it's more, you checked if this or this is larger.
And then
Fill up a point.
you fill it up with like a couple.
Right, so you put all the points in the Brillouin zone. Okay, you can choose here some finite number. And you start filling. The first filled, second, so on.
Up until the square root of 2 pi over a.
Yeah, and then you start showing when it starts to move into the second Brillouin zone, what happens in the corners, and that's that. So you're taking it.
Yeah.
You send me an email with your name so I'll know.
Okay. Will do.
Okay. I'll have a project for the second one also. It's very similar but a bit different. Okay, what's the big difference between here and here?
Type of the potential.
Hmm?
The type of the potential.
The dependence on K is not the same. Right? Instead of just H bar squared, K squared over 2n, I have this E0 minus beta. Oh, these are some constants. Plus, actually minus, right? Not for 8. Was 12 for 3-dimensional, it's 4 for 1-dimensional, it's 8 for 2-dimensional. Okay, so let's assume at the moment that I'm not getting close to the Brillouin zone boundaries. Plus 0, yep. Okay. What happens at small kx and small ky?
It's a circle.
It's a circle because we can expand cosine in the usual Taylor series, and we saw that it basically behaves as a free electron. So here, beginning. But as I fill more and more, it deviates from this behavior. At half filling, actually it looks something like that, straight lines. So it completely lost the free energy behavior. Can convince yourself that if I want here the energy at k, one of the k's pi over a and the second 0 will give me, and I want to keep a constant energy, it will give you a diamond shape. If I continue to fill up, actually you get this behavior even when you don't take into account u. Taking into account u, what is u? Here you'll have to calculate what is E1 minus 1, and it could be a different gamma, but the same behavior, and 1 minus the second at k, at kx and ky equal something here, pi over a and 0, gives you the gap. Okay. But the physics is the same. I'm filling up in the first Brillouin zone until it becomes advantageous to move to the second Brillouin zone. If I have no gap, it will become advantageous once I touch this point. If I have a gap, it might be different. You can see already that if I believe that tight binding is a good description of real lattices where electrons reside, I can get in 3 dimensions very complicated Fermi surfaces. At some point it will go into the second Brillouin zone. It will have spikes in different directions. Once you move from simple cubic to FCC or BCC, it becomes much more intricate. Lovely pictures in Ashcroft, and you can also see in different on the internet, different websites. You will see very nice behaviors. Even you have websites that can feel. Okay, someone volunteers to do this for this behavior, for the tight binding. 5 additional points in the end score of the course. Okay. As Perot said, Nilpima and Nilpim. Okay. Creation and annihilation operators for this tight binding problem. Actually, truth said, I don't even need really creation and annihilation operators, but it's a good exercise to get the basis for writing down and interacting Hamiltonian in these systems, which we won't do in this course. Okay. When I say creation and annihilation operators, basically what do I mean?
The energy levels.
I have to have, even before levels, states, which I can populate and depopulate. Alright? That is a basic idea behind creation and annihilation operators. What are the states that I'm considering here? Well, I'll start from the picture of tight binding and show you that actually it's not different than if I would have thought about free electrons. Okay, so let's draw a lattice. For simplicity, I'll draw a one-dimensional lattice. Okay, and in order to talk about specific boundary conditions, I can have either hard wall or periodic boundary conditions. It makes a difference of one term in the Hamiltonian. Okay. Okay, so I have this one-dimensional lattice. What are the states that I have? Okay, I can have state 1, meaning an electron lives on 1. State 2, state 3, so on and so forth, till state n. Okay. How do I create an electron on state 1? Meaning vacuum, I don't have zero state.
You need some normalization constant.
In this case, no. Why? Because of this. Okay, if I would have been a boson, no problem. I can create 2 bosons on that state, 3 bosons, infinite bosons. For fermions, no, just 1. I try to create another one. It's not allowed. It's a vacuum. Okay, this could be a cumbersome writing because I have different indices for each state. Instead, I could write, and it's very nice to think about and to implement, let's say, on a computer. And so on and so forth. So it's a simple vector that I can write 0, 1, 0, 0, 0, and so on. The first, second, third, so on. Why is that convenient? And the main thrust of it you'll see in advanced quantum mechanics. It's very easy to add more than 1 electron here. Because I can say I have an electron at state 1 and an electron at site 4. No problem. Actually, this is parenthesis, it's above what we are supposed to learn here. This is actually the many-body Hilbert space, which is known as the Fock space. It's just all possible fillings. 0 electrons, which is a vacuum, 1, 2, 3, and so forth. That's how many particle physics is treated in modern language. So I'm taking the notation for there as an introduction to what you'll see further on, but it's also very convenient for what we are considering here. Okay, lovely. Actually, it's nicer than you think, because half of the problem in physics is defining what is your Hilbert space and what are the states that you're working on. Okay. So, after I define a Hilbert space, what do I need?
A complete set.
I have here the complete set. Write down all the vectors, basis vectors between 1 and n. You have a complete set.
You need a Hamiltonian.
A Hamiltonian, exactly. Here I will first approach it from the intuition of tight binding, and then I'll go over and do it from an intuition of a continuous Schrödinger equation. Okay, so let's start with tight binding. What did we write for tight binding? We wrote down E0 minus beta, some constant energy that is in the game. So, in my Hamiltonian, why is that? This you immediately recognize as the number operator. If I have an electron on a site, I get an energy E0. Don't have any electrons, I have no energy. Now, if you remember, we had two contributions in the perturbation theory to the tight binding. Alpha and gamma. One was the overlap between some states on the same site, which was the alpha, and we actually ignored it. And then the overlap between two sites that are nearest neighbor. Okay, I'll write down a term that gives me such an overlap. Okay, so what am I saying here? T is a constant, I'll connect it to gamma once I solve it. First, what is HC? HC Hermitian conjugate, the Hermitian conjugate of this term. Why? Because this is not Hermitian. I'm not allowed to write down a Hamiltonian that's not Hermitian. That's the mathematical explanation. Someone can give me a physical explanation?
Symmetry.
Symmetry. If I'm allowed to move from the first to the second side, there's no reason in the world not to move from the second to the first one. And here I'm just summing up over all points. And here I'm summing up over all points. Okay, so I have a Hamiltonian. Doesn't seem that it got me any closer to a solution, because at the moment I don't know how to treat this term. If I had only this term, it would be trivial. Stick the electron wherever you want and pay epsilon 0, it doesn't matter. Okay, questions still here?
All the interaction is controlled by the parameter t, right?
I wouldn't call it interaction.
Okay.
Why? Because I would call it the kinetic term. And that's actually a good question. Why is this minus and why do I call it a kinetic term? If this would have been plus, it costs energy to move from one side to the other. So I don't do it. So I'm back to a case where if I put an electron on a side, it will stay on this side. Only if it's minus, if I put it on a side, it has incentive to spread out. Spreading out is kinetic energy.
Don't you sometimes want to determine the sign of t?
Yes, but I don't want to go into the... I will show you in a moment that it's the same solution as for the tight binding solution. It can't be anything else, because I put in the terms that play the role in tight bindings, therefore you have to get the same solution. And then where you are close to the edge from the other side, the plus behave. Actually, it's symmetrical plus minus, but conceptually, if I put in low filling, I have to be here in minus. Okay, so that's one way that I got to it. I followed the logic behind tight binding and wrote the Hamiltonian accordingly. I can approach it from a totally different avenue. And that's looking on the usual continuous Schrödinger equation. Okay, so I write down Schrödinger equation. Let's write down a specific form, free electrons. We have seen that although these two Hamiltonians are very different, at the end of the day, we end up with similar behavior. Okay, so nothing else shattering. And then I would stop you and ask, how would you treat such an equation in a computer?
Some sort of discretion of space.
I'm going to a computer, I have to discretize my variables. No matter what computer you are dealing, how much memory you have, you still have a finite number of points, of values that you can stick into your computer. Okay, so instead of speaking about psi of x, I'll discretize it and speak about psi of n. What? Okay, so this side is simple. How do I do a discrete derivative?
Minus.
Subtract one value from the other and divide by the difference, right? So if I'm discretizing space, I have some distance a between 2 points of discretization. What did I do here? The first derivative at 1 point minus the first derivative at the nearby point. Okay? And of course. So this guy is my Hamiltonian, my discrete Hamiltonian. So let's see what these two Hamiltonians actually do. Okay, let's assume I'm writing down here some state 1, 0, 0, 0, and so on. 0, 1, 0, 0, and so on. Okay. 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 And look what's happening here. Will give me 0. Right? This won't contribute because if I'm destroying, let's say, something on 1 and creating it on 2, it's not 1, 1.
The first is diagonal and the second is off diagonal.
And I'll get it for all diagonal terms here.
Actually, this one is only nearest neighbors,
Right? So I can already, without scratching my head too much, know that it's 0 and all other contributions on this line are 0. So here, 3, 1. Well, it has to be the same as permission. So it's 0, so all others here are 0. Where is the only point that I can get non-zero values here?
the nearest neighbor.
On the diagonal one above and one below. All others must be 0. Okay, so 1 H 2 will give me minus T. Here, of course, so I get a tri-diagonal matrix. Okay, so that's the result of this guy. Exchange the same table for what is appearing here. I get the same structure because I always connect something that's at n to something that's at n plus 1 and n minus 1. So these are the only terms in the vector psi n that I connect between them. Again, a tri-diagonal description. Okay, so I've shown that actually from 2 different approaches, I end up with the same matrix. Simple, well, it's not surprising, because what does a discretization of space mean? Putting it on a lattice. Nothing more, nothing less. And why nearest neighbors? Because I took here the definition of the derivative up to nearest neighbors. So, lovely, but what is the solution? Well, I could say, guys, go and diagonalize it on a computer, but since no one of you want to do any work, so I'll do it analytically. And a very nice description that will be the same way that you diagonalize free fields in field quantum mechanics. It's the same thing, because
You can transform it to brass and kets for representation.
that I can do, but that doesn't help me in the solution. What does help me in solution? As usual with any translational invariant system,
You just block here.
even true, but even in a simpler way, I just write a Fourier transform. What did I do here? Somewhat surprising. I do a Fourier transform directly on the operator. But, in a sense, what do I care? I defined the operator. I can do is multiply it by a phase and write another operator which is the sum of the operators that I already know. You ask me what's BK dagger? I wrote you down. You know exactly what it is. How to operate it on some vector in Hilbert space? You know exactly, because you know exactly what this guy does. So you have no problems. So, although it might seem strange, how do I Fourier transform an operator? No problem, I defined it. Okay. Okay. What remains? Let's do the inverse Fourier transform.
You have to remove the dagger from the A.
Right. And pay attention here, I have a minus because it's conjugate. That's BK. What is AI in terms of now I just insert the definition of AI into the Hamiltonian. Nothing more, nothing less. Putting here two operators, AI, dagger, and AI, therefore, and the summation over K is a mute summation, so I should take two different values of K and K prime.
prime, right?
This is prime.
The exponent also.
Exponent also, sorry. This is the first term. Let's divide it, actually do it term by term. So this is I just copied this guy and this guy and wrote down the definition, kept all the summations.
The minuses in the exponents are
Perhaps I switch the minuses.
never mind, but
No, actually I think
above in the first.
the first here I have minus, right?
Okay, okay.
Because it's the inverse. Okay. Looks frightening. 3 summations. Where do I have something that depends on I? Only these guys, right? Nothing else here depends on I. Kroneker's delta. Since we are dealing here with discrete space, it's Kroneker's, not Dirac's. Okay, so we killed the summation. The summation on k has to be k has to be equal to k prime. So I'm left with one summation on k. So this n kills this n. Forgot to copy E0. Okay, so the term that was diagonal in I is also diagonal in K, which is encouraging, but still not a solution, because the diagonal term I had previously. Let's see what happens to the second term. Actually, I'll write the second term as including the Hermitian. Okay. I'll again have divided by n. just inserted the definition of I plus 1 and AI in both terms. Okay. By definition, Ri plus 1 is Ri plus A. So I can pull out the E. Well, I have to be a bit careful. I can remove this guy and put here plus E to the I K A. And here remove the plus 1 and put here E to the minus I K A. Okay. Once I take this into account, I got exactly this delta function that I had previously, right? Because now I'm Ri and Ri integrating over it, and I get K, delta of K and K prime in both of the terms. What is different is, so I have minus T, I get the N from the deltas, sum over only one of the K's, E to the minus I K A, B K bigger bk plus e to the power I k a b bigger k bk again, diagonal in K. Life is good. Same as the tight binding. Exactly the same result. Up to identifying T with gamma. And we have the same connection with the mass and that we met for tight binding. So everything is closed. So what did we do actually here? First, we wrote the same theory in a different notation, got it without the complicated derivation of tight binding. We got it very naturally out of assuming that we are on a discrete lattice and electrons can only hop from one between nearest neighbors. We wrote it down in a notation that will make life simpler if I would like to put into this problem many electrons and interactions, and ended up with the same solution. And learned something about Fourier transforms of operators. Okay. So, there is another chapter about studying the shape of the Fermi surface using a magnetic field. Since we are in a shortened semester and I think semiconductors are more important for the general student, I'll move now to semiconductors. Okay, so the first thing that we have always to remember about semiconductors that at the end of the day they are insulators. Meaning that we have a filled up band a gap, which size we usually use the notation of EG, E gap, and a conduction band. Okay. So, at zero temperature, these are insulators. They're not different than any other insulator if I'm really at low temperatures. Life becomes interesting at room temperature, where
You need that KBT, it's proportional to EG, right?
Once KBT is of order of EG, life starts to be interesting because it's not completely filled up here, it's not completely empty here, so something can happen. Well, and it's a qualitative definition, because how many electrons I have to have in the conduction band in order to be interesting depends on the technology you want to use. So it's not a hard definition, it's just a bunch of materials that behave similarly in room temperature. Now another thing about it. Usually, and that will be not in this lecture, in the next one, perhaps in 2 lectures, it's very important that, how would I say it? Well, actually, it's one of the cases where actually adding impurities doesn't degrade my material, but actually can help me. We'll see why. But for a clean semiconductor, this is the picture. Okay, since we convinced ourselves that the zero temperature behavior is not interesting, but finite temperature is interesting, we have to say something about the filling of the conduction band and the valence band at finite temperature. So how will we do it? Statistical mechanics, that's the only way we know how to treat it. Now, another interesting point, as long as we don't have additional impurities in the system, and we defined it as an insulator at zero temperature, meaning that this guy is completely filled. If I have temperature, any electron that appears here, from where did it come?
From the valence.
From here, meaning
Pairs of
I'm creating here pairs. I'm taking an electron from here, moving it to here, and I get an electron and a hole. Here. It's not that I can't bring electrons from outside. Well, if I'm connecting it to leads, yes, but at the moment, we assume that all electrons that come into the game come into the conduction band, come from the valence band. Okay. So, I sat down, did my tight binding or free electron or whatever approximation I did, and got the density of states for the valence band and the density of states for the conduction band. Depends on material, depends on the lattice structure. Well, lattice structure is material. But I'll here consider it as a given. Okay, before I'm going to do the calculation, somebody knows here what are the most ubiquitous semiconductors?
Gallium.
Yes and yes, but ubiquitous. Ubiquitous is the most common. Silicon, of course.
Silicon.
Thank you. You know, someone is alive. So, actually silicon, germanium, and in some sense also carbon are the most known semiconductors. Carbon is on the limit because its gap is around 4 or 5 electron volts. And for room temperature, it's minuscule transfer of electron. But still, it's once you dope it, put in impurities, interesting things happen for it. So sometimes it's also defined as a semiconductor, sometimes just as an insulator. But germanium and silicon, of course, those are the best known semiconductors, and they have gaps of order of 1/4 of an electron volt, which is exactly suitable for room temperature. All of these are in the 4th column of the periodic table. You have also guys coming in from the 3rd and 5th. That's the things that you mentioned: gallium arsenide, indium, selenium, and well, the most known is gallium arsenide actually for these games. Okay, so basically the number of electrons in the conduction band as function of temperature. I integrate over all the energies between EC and infinity. EC is the bottom of the conduction band. Why infinity? Because at the end of the day I'm still considering relative low temperatures, and it doesn't really matter that I don't take into account the end of the band in the conduction band. Same, I won't care about the end of the valence band. I'll take it to minus infinity. So this is why I'm taking minus infinity to EV. I don't care about the bottom. Why is that? What is the difference between what's written here and here?
That every electron you take from one, you put it in the other.
No, I'm just saying that the probability of having a positive value, that's why it's P and N negative, is 1 minus the probability of that state being filled.
power is on the internal brackets.
Right. Or I can write it down in a simpler form. Little bit of algebra makes sense also from the point of view of looking what's written here. So, what is the big difficulty here? As usual, finding mu. And mu comes out from the conditions that we won't lose or add electrons into the game, so we'll see how to treat it in the next lecture. Okay, tomorrow I think they have this job fair. Anyone here is interested in that? We can start at the usual time. I think we'll start at 12 as usual. Okay.
Thank you very much.
תודה רבה.
בבקשה.
הוא תמיד כאן.